Yeah, so we are live. Okay, so let me check once. Um, so yeah, we are live. So if anyone is in chat, you can drop a hi or anything like that. So we can get confirmation that it's from your end. It's good actually as well. Uh, yeah, it's good actually. I checked. Okay. So, hello everyone, welcome to this session organized from ASDEV Community Kolkata, and I'm Saptarshi, and I'll kind of be your host for this session. And the session is about the basics of deep learning, and we have today with us Somajit Datta, and he has explored various fields like web dev, blockchains, and ML. But actually, I'll let him do his introduction for himself because he will know a lot. So, hi Somajit, I hope you are doing fine.
Yeah, thank you, Shaptarshi. Yes, I am
Yeah,
very fine. Okay,
sure.
so hello everyone. My name is Shomojit. I'm a full stack developer in MERN, and also I've been working with deep learning models for the last 1 year. I have trained numerous models, and now I am also working on a research article on medical image segmentation. And sorry, I am unable to turn on my camera due to bad weather and unfavorable circumstances. Is that okay, Shaptarshi?
Yeah, I don't think that will be a problem. Sure. So, so do I start with the presentation?
Yeah, you can
Um,
start.
okay, sure. Yeah, is it visible?
Yeah, it's visible. Thank you.
Okay. So you just
Okay.
provide me the cue whenever you have to shift, and I'll do it.
Yeah, sure. Okay, starting off with the basics of deep learning. Now, we all know we live in a world where we are constantly surrounded by deep learning algorithms. From social network filtering to driverless cars to movie recommendations, and from financial fraud detection to drug discovery to medical image processing, the field of deep learning influences our lives and our decisions every single day. Now, if you get into deep learning, there is an incredible amount of really in depth information out there. But let's start with the basics, shall we? So, can we go to the next slide, please? Yeah, so what's deep learning? It's just learning from examples. Yeah, that's pretty much the deal. At a very basic level, deep learning is a machine learning technique that teaches a computer to filter inputs like observation in form of images, text, or sound through layers in order to learn how to predict and classify information. Deep learning is actually inspired by the way that the human brain filters information. Coming to the formal definition, deep learning is a subset of machine learning, which is essentially a neural network with three or more layers. This neural network attempt to simulate the behavior of the human brain and allowing it to learn from large amounts of data. While a neural network with a single layer can still make approximate predictions, additional hidden layers can help to optimize and refine for accuracy. Next slide, please. Now coming to the similarities to neuron and the human brain. Um, as we all know, in the human brain, there are about 100 billion neurons, and each neuron is connected to about 100,000 of its neighbors. Essentially, that is what we are trying to create, but in a way and at a level that work for machines. The purpose of deep learning is to mimic how the human brain works in order to create some real magic. Now, what does it mean in terms of neurons, axons, dendrites, and so on? Well, the neuron has a body, dendrites, and an axon. The signal from one neuron travels down the axon and is transferred to the dendrites of the next neuron. That connection, although we know that's not an actual connection, but a connection nevertheless, where the signal is passed, is called a synapse. Now, neurons essentially by themselves are kind of useless, but when you have lots of them, they work together to create some serious magic. That is the idea, and that's what trying to create with a deep learning algorithm. You get input from observation, you put your input into a layer that creates an output, which in turn becomes the input for the next layer, and so on. This happens over and over again until you have your final output signal. So the neuron or a node gets a signal or signals which pass through the neuron and delivers the output signal. Think of the input layer as your senses, like the things you see, smell, feel, etc. These are independent variables for a single observation. This information is broken down into numbers and the bits of binary data that a computer can use. Actually, you need to either standardize or normalize these variables so that they are within the same range. Now, what can our output value be? It can be continuous, like price, binary, like yes or no, or categorical, like separating an animal, identifying an animal, like cat, dog, moose, etc. If it's in categorical data, you want to remember that your output value won't be just one variable, but several output variables. Let's understand again with examples now. Next slide, please. Simple ML models work fine with simple data, but as soon as you want to interpret complex data like an image or an audio or even numerical data with lots of variables like housing prices plus location, number of bedrooms, size, etc., you need something capable of dealing with that complexity. These simpler models are connected into layers, and this is where the depth of deep learning comes from. In reality, a neural network is a big, complex mathematical function which looks nothing like what you see here, but the diagram may help you to see what's going on. Like any other machine learning system, a model is trained with data fed into the model, and it attempts to make a prediction. At first, the prediction will be essentially garbage, but the feedback is used to improve the model. Now, once the prediction quality is sufficient, the model is tested with new data and it makes a prediction based on what it learned from the training data. What the diagram doesn't show is how the neuron is able to learn and improve on its feedback. Let's look more deeply at how a neuron is able to make a decision. Next slide. Researchers describe this field of machine learning less like engineering and more like scientific exploration. For example, for a long time, the sigmoid activation function was used until the ReLU function was discovered to be more efficient and effective than for many situations. It's not necessary to know all the mathematics behind the machine learning in order to use it, but it's shown here to reinforce the concept that machine learning is and its core as a complex mathematical function that is trained to do well on a particular goal. Now, next slide, please. Now, it's a visualization of how an activation function basically works. Now, when we apply a activation function to a neuron, I mean, this is a mathematical way of setting the threshold or a condition for activating a neuron. You can, I mean, this is kind of similar to if else statements in programming, like if time is greater than 11 a.m., then eat lunch. The neuron checks to see if the input value meets the activation function's requirements. If it does not, then do nothing and pass no value onto the connected neurons in the network. Now, if it does, do something to the data and pass the result as an input to the next neuron. This operation is carried out across all the nodes and the network, allowing it very complex patterns to be learned and predictions to be made. Next slide, please. So, a neural network can be comprised of many hidden layers. These are intermediate steps to get the prediction to the output. For example, a neural network may have layers to detect certain colors and shapes, and other layers to differentiate between certain types of animals and breeds. It's important to clarify that the neural network does not know what a dog or a cat is. It's just learning to do what we want it to do based on the feedback and the pattern it detects automatically. But how does a neural network learn from feedback? Well, neural networks are loosely modeled after the biological brain, as we discussed before. The connections between neurons can be strengthened and weakened using weights and biases. For example, when a dog receives a treat and a pat on the head for retrieving a ball, it is more likely to do that again. Weights and biases allow a neural network to learn what pathways work for a certain task and the bias the network to use those pathways again. This makes the network more effective and efficient at making predictions. Now, all of these complex calculations are accomplished far more quickly and often than a human could ever hope to. It requires a lot of computing power to achieve quality results, which is why neural networks were once thought infeasible, but now data centers, also known as computing clouds, with greater processing power, make neural networks a reality. Next slide, please. Okay, so there are three types of deep learning models. There can be like supervised, unsupervised, and reinforcement. Now, for supervised learning, consider yourself as a student sitting in a math class wherein your teacher is supervising you how you are solving a problem or whether you are doing it correctly or not. This situation is similar to what a supervised learning algorithm follows. That is, with input provided as a labeled dataset, a model can learn from it. Labeled dataset means for each dataset given, answer or a solution is given as well. This would help the model in learning and hence providing the result of the problem very easily. Now, in case of unsupervised deep learning, as you saw in deep supervised learning, the data set is properly labeled, meaning the set of data is provided to train the algorithm. The major difference between supervised and unsupervised learning is there is no complete and clean labeled data set in supervised learning and unsupervised learning. And coming to reinforcement learning, um, it is based on neither supervised nor unsupervised learning. So, to be straightforward, in reinforcement learning, algorithms learn to react to environment on their own. To be a little specific, reinforcement learning is a type of learning based on interaction with the environment. It's rapidly growing along with producing a huge variety of learning algorithms that can be used for various applications. Basically, if you are into game development and stuff, this is, I mean, reinforcement learning is used basically. The next slide, please. Okay, coming to the examples and application of deep learning. The first thing is entertainment. Deep learning has benefited the process of creating, publishing, and delivering entertainment media. Analysis of human body language through cameras had made modeling virtual characters easier. Deep video analysis has made the process of editing, video sync, and transcriptions faster. Filmmaking is revolutionized thanks to deep learning. Streaming services and social media platforms make use of deep learning. It helps them offer a more personalized experience to the end user. From recommendations to advertisements, deep learning facilitates the best targeting. Netflix, Amazon, YouTube, Facebook incorporate deep learning in the algorithms. Sports entertainment too reaps the benefit of deep learning. Analysis of player emotions, audience response help pick the best highlights from hours worth of footage. Next, coming to virtual assistants. Virtual assistants today are empowered as a human at your back end call. They can take notes, perform actions, and even offer suggestions at your voice's command. Our virtual assistants can make use of deep learning to extract data from us, right from our voice, accent, places we visit, to the songs we love. They know it all. This helps them get better and more personalized to your needs over time. Visual recognition. Deep learning models can identify and sort images based on location, items, and even people. Image analysis for obscenity on social media platforms help create a safer environment for all. Visual recognition helps access the right images from the vast libraries of search engines. It also sorts images on your galleries so that you can find what you need very quickly. Now, face recognition has been used in security application for years. Smartphones too now also now unlock by recognizing your face. These revolutions are all thanks to deep learning. Now, healthcare industry is also a prime example of the contribution of deep learning towards making human lives better. Over the years, GPU-based systems have made the job of healthcare workers very easy. They have also contributed towards efficient diagnosis, standardized treatment, and overall better performance. Deep learning has empowered healthcare systems to address a shortage of quality workers, conduct accurate early stage diagnosis, offer better pathology reports, predict outbreaks or epidemics, standardize the route of treatment, develop new drugs and vaccines, etc. Deep learning is increasingly used for research purposes. Many healthcare giants are also adopting these deep learning models to offer faster, better treatment and reduce costs. The next big thing is natural language processing. The analysis of text or speech and its comprehension to offer the right output is called natural language processing, or NLP in short. The complexities and nuances of human language are endless. Hence, systems like deep learning that learn and improve as they go have the upper hand. NLP is being accepted in some summarizing long form reading materials like legal documents. They also help in classifying text, analyzing sentiment, and answering questions. Customer care and experience chat tools have also found an excellent use for NLP. The ability to understand complexities and even build phrases independently allow bots to perform well, with excellent efficiency. Fraud detection. The banking and the finance sector is no stranger to fraudulent transactions and scammers. The adoption of deep learning based security systems has helped add an extra layer of protection. Models identify patterns in customer transactions, keep track of credit scores, and raise the alarm at the sight of anomalous activity. Such implementations have helped credit card frauds and saved money in recovery and insurance. Self-driving cars. This is an idea that was once made appearance in fantastic dreams. Self-driving cars have now more of a reality than ever. But what fuels this spectacular feat humans are so close to perfecting? Yeah, you have guessed it right. Deep learning. A multi-layered web of deep learning algorithms brings driverless cars to life. Self-driving cars can identify signage and paths, maneuver through traffic, and even accommodate real-time elements like road blockages. This is all made possible through data from cameras, sensors, and geomapping. Research continues to enhance our deep learning models to perfect self driving vehicles. Driverless cars are said to solve many human like challenges. They can be used to transport as well as commercial deliveries, among many use cases. Okay, to the next slide, please. And lastly, the deep learning in the future. The future is full of potential for anyone interested in deep learning. The most remarkable thing about a neural network is its ability to deal with vast amount of disparate data. That becomes more and more relevant now that we are living in an era of advanced smart sensors which can gather an unbelievable amount of data every second of every day. It is estimated that we are currently generating 2.6 quintillion bytes of data every day. This is an enormous amount of data. While traditional computers have trouble dealing with and drawing conclusions from so much data, deep learning actually becomes more efficient as the amount of data grows larger. Networks are capable of discovering latent structures within the vast amount of data, unstructured data like raw media, for example, which are the majority of data in the world. Okay, thank you for the session. This is the end.
Okay, so can I turn the screen share off, right?
You can.
Okay. Okay, so I think that was very helpful and very informative. So
Yes.
we can go to, I mean, in the chat there are questions, right? So Arya has asked, why do we use every neuron in the previous layer with the current layer? We can remove some of the redundant connections and make the algorithm computationally less expensive.
Yes,
So we
you can,
can show that
but
on the screen.
yeah, but that would defeat the very purpose of our, accurate predictions, right? So if you want more accurate predictions, you need to train more neurons. You need to keep more neurons in the layers to give accurate information. That's all. Now, if we remove the that connections, then how can we expect precise data, precise output?
Okay, so yeah, so Mojit, we are also seeing you. So if you are still with us and enjoying the session, you can drop another text. Okay, so next, actually, I have a question too.
Yeah.
Um, the when I first started getting into deep learning, and I still have that question still now. So anything I saw was can be converted to a problem statement, right? Like whatever I see can be converted to a problem. When do we judge that a problem statement is can be validly solved using deep learning and cannot be? So when do we differentiate that?
Yeah, this is actually a very good question. Actually, the thing is, to train a deep learning model, you need huge amount of data, right, to train the model.
Yeah,
Now, if you don't have this amount of data, you can't train a model. But that also differs with supervised, unsupervised learning. Suppose you want to make a kind of a recommendation system, like a movie or something like that. So
yeah,
you need not, I mean, get all the data. I mean, you need not require the data to do that. It will just gain from what you do. I mean, while
mm,
the application is being used. But if you are training models for like supervised learning, you need to have very vast amount of data, and if it's not available, then you can't. You simply can't.
okay. So um, I don't think there are any questions anymore. So I think um, I would like to ask you next to provide any kind of guidance or roadmap on how to, how mean new people can start with the domain. I think how a basic roadmap would be good.
Okay, sure. To start with deep learning, you need to clear the basics of machine learning first. Like we need to know the, I mean, simple terms like linear regression, logistic regression, starting with that, and you have to dig deeper into the mathematical formulas and stuff. Now, if you are not clear with those, you will have troubles understanding the deep learning models, the activation functions that we use in every layer, right? So if you start with this and you carry on, then also you need to know about what regulation does, right, in linear regression. You must know Saptoshi, right?
Yeah, yeah.
Yes. So after you're done with this basic stuffs, then you can move on to artificial neural networks, the basic thing, as we call it, the perceptron, the single layer artificial neural network.
Mm.
Then, I mean, you can just see how it works. You can do simple projects like the hotel price classification and stuff, and then you can just move on to CNNs or RNNs for that matter.
Okay. So I think that would be it. And thank you for the session once again. And I hope we can make this to a series. I mean, to an complete end-to-end series somehow. So I think that would this would be a great start for that too. So thank you for joining us today and sharing your exceptional knowledge. Thank you.
Yes, thank you. Thanks a lot, Satoshi.
Sure.